get started. So in exercise 4.9 part 9, guys. Yeah, in exercise 4.9 in exercise 4 part 9, there is, I say that G is a group with P to the n elements, and I forgot to say P is prime. So thanks for the person who brought this up. P should be prime, okay? Otherwise it doesn't work. Of course, for psychological reasons, we all use P to denote a prime number, okay? Yes, sir.
But if it's prime, doesn't that mean it's not a general group? It has to be.
Yeah, it's a specific group.
Huh?
It's a specific group with P squared element, P cubed element. It's not any group. It's a group with P to the 4 elements. Okay? How was the homework, by the way? It's lighter than before, right? Yeah, okay. I'll try to make it a bit lighter every time. But again, but it's important, please, okay? Okay, great. So last time what we saw, we were talking about left and right cosets. So let G be a group. And H a subgroup of G. This is a small, okay, yeah. So we define the left relation, we call it L. X is related to Y, if and only if Y inverse X belongs to H. And the equivalence class of an X in G is just the left coset XH. And we know that if I have two cosets, G1H is equal to G2H, if and only if G2 inverse G1 belongs to H. Also in the same way, GH is equal to H, if and only if G belongs to H. Okay? Yeah? Cosets partition. Cosets partition the group G, since they're equivalence classes. Two cosets are either disjoint or equal. And then the index, the set of left cosets is denoted by G modulo H. Okay, left modulo H. Great, now let's look at the right cosets. The right cosets are equivalence classes of the following relation. The equivalence class of an X in R is a left coset. And we have that HG1 is equal to HG2 if and only if G1 G2 inverse belongs to H. Right? And then HG is equal to H if and only if H. The set of right cosets is denoted by G modulo H, but yeah. And we know that there exists a bijection from G mod H to H mod G. It's a well-defined bijection. And then the index of H and G is the number of left or right cosets, because the two numbers are the same. We denote it by G H. And if G is finite, finite. Okay. The index of H in G is equal to the cardinality of G, or the order of G divided by the order of H. Okay? Remember this, everybody? This is basically a small recap of cosets. Okay, now how, if I have a group and I have an actual subgroup, how do I compute the cosets of that? I'll do an easy one. Well, I'll do first. Okay. Let's give ourselves a group. Consider the group Z with addition. Of course, Z is a group under addition. And the subgroup NZ. Okay, what is the subgroup NZ? It's just all the multiples of n. So it's Kn as K is in Z. Do we agree that this is a subgroup? So all the multiples of n. Is 0 a multiple of n? Is 0 a multiple of n?
Yes.
0 is 0 times n. Great. Now, if you take a multiple of n and add it to a multiple of n, do you get a multiple of n?
Yes.
Yep, that's clear. Now, if a multiple of n, then is its additive inverse a multiple of n? So if x is a multiple of n, is minus x a multiple of n? Yeah. So nz is a subgroup. nz is a subgroup of z. This is clear. Now, what are the cosets? Here. The cosets are the equivalence classes of the following relation. The left cosets say, I mean here since z is abelian, left and right cosets are going to be the same, right? We did this remark before, we mentioned this remark before, but let's ignore it for now. So the left cosets are the equivalence classes of the following relation. Okay, remember, I mean, I'll write it down here. In multiplicative notation, left cosets are the equivalence classes of this relation in multiplicative notation. Okay? Yeah? In additive notation, this times becomes a plus, right? This circle here, I mean, I said I'll be dropping circles. This circle become a plus. And this y inverse, what does it become? Minus y. Right? For the following relation. If and only if minus y, doesn't matter here, minus y plus x, or x minus y, belongs to nz. What do I find here? X minus y belongs to nz, means that x minus y is divisible by n. Right? X minus y belongs to nz, means that x minus y is a multiple of n, which means that x minus y is divisible by n. Do I know the cosets of this equivalence relation? We have seen them before, right?
Yes.
These are the integers modulo n. How many equivalence classes do I have here? N equivalence classes. What are they? I say 0, 0 plus nz. Equivalence class of 1, 1 plus nz. And so on, the equivalence class of n minus 1, which is n minus 1 plus nz. These are the same equivalence classes of the congruence relation modulo n. Right? This is just the congruence relation modulo n. Right? So we generalize the subgroup, we generalize this congruence relation to modulo n to a more general notion. If I have a group and I have a subgroup, here my group is G and my subgroup is H. In particular, if my group G is Z and my subgroup is NZ, the multiples of n, I get back my congruence modulo n. Now what is the index of NZ in Z? How many left cosets do I have? N left cosets. So the index of NZ in Z is n. Is Z finite? Is Z finite? No. And NZ is not finite either. So, but the index of Z in NZ is finite. Okay? Great. Any question? Any question? So really, what we found here is that this relation is just the congruence relation modulo n. Okay? Great. Let's do one more. This is the nice example. Let's do an example that is harder. Compute the cosets of H, identity, 1, 2, 1, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 2, 2, and S4. Now, first I need to check that H is indeed a subgroup. How do I do that? Can you spot this quickly? Why is H a subgroup? H is a subset of S4, right? We agree that H is a subset of S4. Now, why is it a subgroup of S4? Yes?
Well, all its elements are in S. Then you have the identity element that is just thing. Of course, if you multiply compose any of them, right?
It's not, well, it's not, of course.
It's a composition, you get another of them only.
Yeah, but why of
Then,
course?
huh?
You have to check it. Why of course?
Because, wait. S3 is contained in S4,
Exactly.
right?
So really,
And so when you do a bijection between only 1, 2, and 3, the 4 doesn't change.
exactly.
But since this is also a group and it's only within S4, it works in the same way, right?
That's right. Very good. That H really is just the symmetric group on 1, 2, 3. Right? So you can view the symmetric group on 1, 2, 3 as permuting 1, 2, 3 and leaving 4 fixed. 4 is fixed. So this is really a subgroup of S4. H is really S3 here. Right? Write down the symmetric group on 1, 2, 3. This is what you get. Okay? H can be realized as the symmetries of 1, 2, 3. Great, so H is a subgroup of S4. Okay, now, how do I compute the cosets? First of all, how many cosets do I have? S4 has how many elements? Yes, sir.
I'm sorry, what's S, Y, R, M?
S, symmetries.
What is, I don't understand.
Symmetries is the set of bijections from X to X. right? The symmetric group on X is the set of bijections from X to X. Yes, sir.
I'm still like a little confused why you like denoted the fact that H is like can be this like the subgroup because if I remember correctly, one of the conditions of subgroups was if an element is well in the subgroup, then its inverse is also in the subgroup as well.
Yeah.
So like for example, like if we take one of the elements, like let's say 1, 2.
Yeah.
Where's the inverse? Like
1, 2. What's 1, 2 times 1, 2? Yeah. So the inverse of 1, 2 is 1, 2. The inverse of 1, 3 is 1, 3. The inverse of 2, 3 is 2, 3. The inverse of 1, 2, 3 is 1, 3, 2. The inverse of 1, 3, 2 is 1, 2, 3. Okay? Yes?
You said the symmetric group is the set of bijections from X to X.
Yeah.
So in this case, what is it's from what to what?
From 1 to 3 to 1 to 3. H.
Okay.
Right? H is all the possible bijections from 1 to 3 to 1 to 3. Okay? Okay, now first of all, how many cosets do I have? How many, the left cosets here, let's write the left cosets. How many left cosets do I have?
4.
4 left cosets. Why is that?
Well, because there's 6 elements in H and there's 24 elements in S4, so
Exactly.
you divide them.
There are. The number of elements in S4 divided by the number of elements in H, 24 over 6, which is 4 left cosets of H. How do I find them? Great. What's the first left coset of H? Pick an element, multiply by all the elements in H, you get a left coset. What's the first thing to do? What's the easier thing to do? Yes? Identity times H. So the first left coset is always for free. H. Well, let me write it down. The first left coset is H. H, or the identity times H. This is the identity. 1, 2. What the heck would I write? 1, 2, 1, 3, 2, 3, 1, 2, 3, and 1, 3. Great. How many do I have left? I have 1. How many do I have left? 3. Great. Now, how do I find that? What do I know about cosets? First of all, I know that cosets partition the set G, the group G, and that 2 cosets are disjoint or equal because they're equivalence classes. Now, to find another representative, so to guarantee that I get a different coset, I should not, yes? Exactly. So I pick an element in S4 that I do not see here. Now I can do this calculation. Do you want me to do this calculation and convince you get the same thing or not? Should I do it?
Do it.
Yeah, let's do that. I mean, 1, 2 times H. 1, 2 times the identity is 1, 2. 1, 2 times 1, 2 is the identity. 1, 2 times 1, 3. 1 goes to 3 and 3 stays fixed, so 1 goes to 3. And then 3 goes to 1 and 1 goes to 2. Let's double check. 2 goes to 2. Yeah, very good. 1, 2 times 2, 3. 1 stays fixed and goes to 2. And 2 goes to 3. Stays fixed. 3 goes to 2 and 2 goes to 1. Awesome. 1 goes to 2 and 2 goes to 1, so 1 is fixed. 2 goes to 3 and it's fixed. 2, 3. 3 goes to 1 and 1 goes to 2. That's good. And then here you have 1. 1 goes to 3, is fixed. 3 goes to 2, which goes to 1, and 2 goes to 1. Okay? You get the same set again. You see that? Is that expected? That's expected, right? You get the same set again.
Because
So-
that element is inside.
Exactly, because 1, 2 is already inside, so 1, 2 times H will be equal to H. Okay? Great, so I have to pick another element, so this element is no good. I have to pick one more. So I have to pick an element in S4 that is not in H. Let's pick something easy. So I will pick
1/3.
1, let's see, let's pick 1/4 for example. Okay, I'll erase this one so that I have some space, okay? 1/4 times h. Okay, 1/4 times h. It's 1/4. 1/4 times 1, 2. 1 goes to 2 and 2 stays fixed, so 1 goes to 2. 2 goes to 1 and 1 goes to 4, so 2 goes to 4. 4 stays fixed and goes back to 1, that's good. Now 1/4 times 1, 3. 1 goes to 3 and 3 stays fixed. 3 goes to 1 and 1 goes to 4. 4 stays fixed and goes to 1, that's good. 1/4 times 2, 3, you really can't do anything. This is the best possible way you can do it. 1/4 times 1, 2, 3. 1 goes to 2 and 2 stays fixed, so 1 goes to 2. 2 goes to 3, which stays fixed, so 2 goes to 3. 3 goes to 1, which goes to 4. And 4, let's double check. 4 stays fixed and goes to 1. I'm good. 1 goes to 3 and 3 stays fixed, so it's 1 to 3. 3 goes to 2 and 2 stays fixed. Let's double check that 2 goes to 4. 2 goes to 1 and 1 goes to 4, so that's good. 4 stays fixed and goes back to 1. I'm good. Okay? Are we good? Yes, sir.
I don't really understand like how you started like getting all those elements. Like you wrote down 1/4 next to it.
1/4 times the identity. 1/4.
Right.
1/4 times
okay.
1, 2, 1, 2, 4. Right? Yes, sir.
So to find all of the cosets, would we just have to guess and check and like keep continually, would we just have to continually keep on doing less multiplication to
Exactly.
and
Exactly.
just like because there's going to be some overlaps, right? Like
Is there?
4 might be the same as
Yeah, but so here, how did we avoid that the coset of 1/4 is not h? I pick an element in S4 that is not in h. I am guaranteed not to have the same quotient.
but then what does that logic continue to extend?
Exactly. Now, how many cosets do you have left? I have 4, I have 2. How many do you have left? So I need to find a representative. Now my representative have to not to show up here and not to show up here.
Because if they show up in the second one, they'll already be in.
Exactly. You have to pick an element in S4. You know that two cosets are disjoint or equal, right? So if you pick an element here as your representative, then you will get this coset back. So let's pick an element that did not appear. And yep,
You can pick 2, 4 instead.
let's pick 2, 4. Very good. Do you see a 2, 4? I don't see one. 2, 4 times the identity, what do you get?
2, 4.
2, 4. 2, 4 times 1, 2. 1 goes to 2 and 2 goes to 4. So you get 1 goes to 4. 4 stays fixed and goes back to 2, so 1, 4, 2. Let's double check. 2 goes to 1 and 1 stays fixed, so 1 goes to 2. Great. 2, 4 times 1, 3, you really can't do anything. This is the best you can get. 2, 4 times 2, 3. So 2 goes to 3, which stays fixed. 3 goes to 2, which goes to 4. Right? Let's double check. 4 goes to 2. Very good. 2, 4 times 1, 2, 3. 1 goes to 2 and 2 goes to 4. 4 is fixed and goes back to 2. Great. 2 goes to 3, which stays fixed. Let's double check. 3 goes to 1 and 1 is fixed. That's good. 2, 4 times 1, 3, 2. 1 goes to 3 and 3 stays fixed. Great. 3 goes to 2, which goes to 4. 4 is fixed and then goes back to 2. Let's double check. 2 goes to 1, 1 stays fixed, so I'm good. I found one. Now the remaining coset, what I can do is just say the remaining coset is S4 minus the union of these three. Because I know that the cosets partition the group. I already have one coset left, and I have the 3 other ones. So it's S4 minus the union of these 3. But let's pick a representative of the coset and do it. What do you suggest? Does 3, 4 appear here? 3, 4 does not appear. Okay? Should I do the calculation? Should I do it? Or I'll do it, okay? So 3, 4, 3 goes to 4. Okay. 3 goes to 4. 1, 2, 3, 4, you really can't do anything, you just have to keep it this way. 3, 4, so 1 goes to 3, 1 goes to 4. 4 is fixed and then goes back to 3. 3 goes to 1, stays fixed, that's good. 3, 4 times 2, 3. 2 goes to 3, which goes to 4. 2, 4. And then 4 stays fixed, which goes back to 3. 3 goes to 2, that's good. 1, 2, 3 times 3, 4. 1 goes to 2, it's fixed. 2 goes to 3, then 4. Let me check. 4 is fixed, and then goes to 3. 3 goes to 1 and 1. So it's very good. Then I have 1 left. 3, 4, that was 1, 3, 2. 1 goes to 3, and 3 goes to 4. Yeah, and then I have a 3. Then I have a 2. 3 goes to 2. Okay? These are the left cosets. Now if I tell you, what is What is 142 times h? If I tell you find me 142 times h, are you gonna multiply the whole thing again? What is 142 times h?
Well, like 142 up here is there, so it's like the same as 2, 4.
Exactly. I don't know where there is, but I trust you mean this one. So 142h will be 2, 4 times h. Right? You don't have to compute it. What is 143 times h? What is that equal to? Where do you see a 143? Here. So this is equal to 3 fourths. Okay? Is it clear? Is it good how we compute cosets? This is how you should go about it. Okay? Great. Especially if you find, now here there's a quick way of finding the representative. But yeah, I mean here I knew what the representative are going to be. In this case, the representative can be chosen nicely, and I expect what each coset will be. But in general, there is no way to find it. Okay? You just have to go through it. Great. I mean, notice just something for you to think. You know, when you're at home, notice like every permutation in this particular case, every permutation sends 4 to 1. 4 goes 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 to 1. Great. Every permutation here sends 4 to 2. It's not true for any subgroup. I just picked it on purpose to be. Okay? Just think about it. Why? Try to prove a more general case, for example. Okay? Great. Anyways, but this is how you should compute cosets in general. I mean, in the assignment, I give you 2 groups, 2 or 3 groups, 2 or 3 subgroups, and I tell you compute the cosets. Please do it, okay? Even though it's not graded, but please do it. Okay, great. We're done. Are we good with coset? Yes, sir.
For the homework, there really are just 2 questions that are graded.
No, 2 questions are graded, and 2 more which I'm gonna tell you which. Okay. So I tell you which 2. I tell you already two that you work on, and I tell you.
So like 2 mystery questions we don't know.
Yeah, well, but from exercise 4.
Okay.
Right.
Yeah.
So if we do entire of exercise 4, we get everything.
Yeah, you should do the exactly. So like, yeah. I mean, I don't want anybody to not understand what I was doing. So I said that I will give you 2 questions that are going to be graded. So there are 4 parts. There are 4 parts that are going to be graded. I will give you 2 of them, and 2 of them I will choose. Okay?
So we still need to do everything.
No, 2 I will tell you that are going to be graded, and 2 more that are going to be graded that I won't tell you which ones.
So you should.
It's all from question 4. Yes.
Oh,
Okay?
So do I just hand
From exercise.
everything from question 4?
No, I will post a. I'll post a.
Oh, it's out of it.
Yeah, you hand in everything from question 4. Yes.
So if you wanted to do the right cosets, you should do each time. Like,
Exactly. Well, I mean, yeah, you have to. You start in the same way. They're not necessarily equal to each other. You start h times 1, 4. What do you get? H times 2, 4. What do you? Okay. The same way.
and left cosets are not.
They're not. You don't have any terms on right and left cosets. You know that they have the same. The cosets have the same size, but you don't know anything about them. Okay. Yeah. Okay, are we good here? Great. Should I do the right cosets or that's okay? The right cosets, you do it the same way. You pick an element that you don't see previously. You pick an element that you don't see previously. You pick an element that you haven't seen previously. And that's how you do it. Okay, great. Now, let's start a new thing. We'll start a new section called Cyclic Groups. Now, I read the book a bit. We're going to do it a bit differently. I mean, I think I'm going to prove everything about finite cyclic groups. Okay, so usually you see that in Algebra 1 and in Algebra 3. But it's nothing really difficult, so I'm going to do it entirely. But it's not bad. Actually, it's not bad. Cyclic groups. Okay, this is the title of the section. I mean, again, we have done everything. We have done almost everything that we need. So like, we just finish this. Okay. So I mean, the first part, subgroup generated by G. This is the title of the big section. This is a small section. So let G be a group. And let G be in G. Denote by G in angled brackets. So the set G to the n as n is in Z. Okay? So you have G, G squared, G cubed, G4, G5, G6, G7, G8, G9, G101, G minus 10 million, G, okay? All the powers of G, including negative powers.
But negative powers, that means you
The
inverse
inverse,
it.
exactly, the inverse of the positive. Exactly. I claim that this literal G is a group, is a subgroup of G. Literal G, angle bracket G, is a subgroup of G. This is clear, right?
Yeah.
Claim literal G is a subgroup of big G. Okay, let's prove that. So the identity of G is G to the power 0, right? Yes? So the identity is there. Now if I take G to the n1 times G to the n2, what do I get? I get G to the n1 plus n2, right? Which is also in little g. n1 in Z, n2 in Z. This implies that n1 plus n2 is in Z. Okay, now if I take the inverse of G to the n, is G to the minus n. Right? Which is also in there. Are we good here? So G is a subgroup of G. Is it clear? Is this clear? Everyone, is this clear? So G is a subgroup, so angled bracket G is a subgroup of G. Little g is a subgroup of G. let's give an example. I'll give an abelian group here, okay, where the thing is addition. So for example, the subgroup generated by 2 and Z. This is just all, when I say power, when I talk about addition, is just the multiples of 2, right? It's just 2k. It's 2, the operation applied k times, or minus k times. Minus k times being the inverse of k times. So really it's just 2k as k is in z. Right? In Z, the subgroup the subgroup 2 brackets is just 2Z. Any question? Yeah? Are we good here? Great. I mean, let's pick a multiplicative number. They're generated by, let's say, 3 n r minus 0 with respect to multiplication. What is that? Well, really, you cannot do anything about it. This is just 3 to the n as n is in 10.
Didn't you say multiplication?
Oh, sorry, yes. Or division is multiplication. Right? Okay? Yes, sir.
Can we just update that as 3 to the z inverse?
No, well, yeah. I prefer this one, okay? But saying like 3 to the z. I've never seen that, but yeah. Okay? Great. Now, we call G the subgroup the cyclic subgroup generated by G. Okay? Yes, sir. The angle, just, it's a notation. That's how I call it. This set, I call it this way. Okay? Is the cyclic subgroup generated by Z. Okay? Generated by G. Great. Now another claim, in the sense that if H is a subgroup, I'll let you prove this as an exercise, and this is not very hard, and G is in G, then G is a subgroup of H. So if you have a subgroup H of G that contains little g, then H must contain the subgroup generated by G. Okay? This is clear, right? If H is a subgroup of G and G is there. Oh man, it's done. Okay, so I'll see you guys later.